an enigmatic traveller, 3i Atlas, has slipped through our cosmic neighbourhood, an interstellar intruder carrying whispers of other suns. Some astrophysicists suggest it might be a planet maker, a seed that can help birth worlds by stirring dust and ice into something larger. Tonight, we'll drift beside it, unravelling how such visitors could spark new solar systems, and what that means for our own place among the stars. Imagine looking up into a night so clear that every star feels close enough to touch, and then realising that one of the lights moving ever so slightly across that canvas is not from here at all. It is a messenger from another sun, a wanderer that has slipped loose from the gravity of its birth star and sailed for untold ages through the cold between worlds. We call it 3i Atlas. The 3i marks it as only the third confirmed interstellar visitor ever seen in our skies, following Oumuamua in 2017 and Borisov in 2019. Atlas honours the survey that first spotted it. That little string of letters and numbers carries a big story. This object began elsewhere, far beyond the slow snow globe swirl of our own Oort cloud, and its path through our neighbourhood is a once-in-a-generation chance to learn how other planetary systems are built. When astronomers call something interstellar, they're not just being poetic. They check the shape of its path around the Sun. Things born here are bound here. Their orbits are circles or ovals that loop back on themselves. 3i Atlas doesn't loop. Its track is a hyperbola, open-ended like a slingstone skimming past a campfire and heading off into the dark. The numbers say it's moving too fast to be captured, with an excess speed that guarantees it will not become a long-term member of our solar family. Even before anyone measured its composition, the trajectory itself told the tale. This visitor did not come from us. It came from away. The discovery felt a little like catching a whisper. The Atlas survey scans the sky for things that change, new blips, faint streaks, objects that move against the fixed background of stars. On a July night in 2025, that whisper became a signal, and within a day, checks against follow-up observations and orbit calculations made it official. Interstellar. From there, telescopes north and south pivoted to watch, to measure, to squeeze as much story as possible from the faint light shedding off its haze. In the weeks that followed, images began to show the soft glow of activity. A coma, even hints of a tail, like frost steaming off a traveller's coat as it stepped into sunlight after a long, cold road. Because it is active, 3i Atlas looks fuzzier than a star in a telescope eyepiece. That fuzziness is its coma, a cloud of dust and ices that were locked tight in the nucleus during the long interstellar journey and are now sublimating as the sun's warmth reaches them. Dust lifted by escaping gas spreads out and, pushed by sunlight, starts to trail in a tail that can grow as the comet swings inward. The beauty is practical too. The coma and tail act like a billboard advertising what's inside. Split the light with a spectrograph and you can read the gases and grains clue by clue to figure out which kitchen baked this object. What star's nursery, what chemistry, what temperatures, what history. Early looks have already hinted at familiar comet ingredients and the telltale signatures of vigorous outgassing, the kind of behaviour that helps confirm we're not just seeing an inert rock but something alive with volatile ices. Speed adds its own kind of drama. 3i Atlas is tearing through our neighbourhood fast, faster than most comets we know, because nothing is holding it here. It will swing by the sun, reach its closest point, and then leave on nearly the mirror image of the path by which it came. On the way in, the increasing solar heat should grow its coma and tail. On the way out, that activity will fade as the chill returns. For us, that means a tight window to observe as much as possible. Watch how its glow changes with distance, how its dust behaves in the solar wind, how its gases flare or subside. For science, the timing is gold. Orbital geometry, sunlight, and a crowd of telescopes all line up to turn a faint intruder into a bright lesson. Then there's the question that makes this visitor more than a curiosity. What does a piece of another planetary system look like up close? Oumuamua arrived enigmatic, likely not even a classic comet, with strange non-gravitational accelerations and no obvious coma. Borisov, by contrast, behaved like a normal comet, and then fractured. 3i Atlas gives us a third data point, a fresh roll of the dice. If its makeup resembles comets from our own deep freeze, that hints that planet-forming kitchens across the galaxy stock similar shelves. If it's different, richer in some ices, depleted in others, or carrying exotic molecules, then we get a taste of variety. Either way, we learn about the raw materials that build planets, and perhaps the kind of ingredients delivered to young worlds by swarms of objects like this one. Even its direction of arrival tells a quiet story. Trace 3i Atlas backward and you point roughly towards Sagittarius, in the crowded starfields near the Milky Way's centre, an origin on the sky that isn't what early models would have guessed for the easiest interstellar interlopers to find. That surprise matters. It compels astronomers to revisit their expectations about where these objects come from, how often they should appear, and how our surveys can best catch them in the act of entering the solar system's light. Each new interstellar object doesn't just expand our catalogue, it recalibrates our search image for the next one. For all the excitement, there is reassurance too. 3i Atlas is no threat. Its path misses Earth by a comfortable margin, and the closest approach to the Sun is just a seasonal marker in an orbit that never closes. Think of it less like a bullet and more like a distant ship seen from shore. Beautiful, fleeting, and gone again before most people even know to look up. If you do look, you're joining a global campout of professionals and amateurs who will follow it through the end of the year and into the start of the next, collecting light curves, spectra, and images that will become part of the shared story of how planets might arise from dust and ice. And nestled inside that calm observational campaign is the thought that headlines love but science treats carefully. Could wanderers like this help seed other systems? The idea isn't magic, it's mechanics. A fast passerby perturbs dust, sprinkles exotic grains, delivers ices or metals that a young disk might lack, nudges pebbles into denser streams where they can clump. Even if 3i Atlas is just one mote among billions, each encounter is a chance event in a galaxy that runs on chance events. Planet formation is a story of tiny assists accumulating into worlds. An interstellar visitor can be one of those assists, small perhaps, but real. Whether 3i Atlas itself has such power is exactly the kind of question that careful, patient observation can begin to answer. So picture it now, a dim, soft star with a breath around it, sliding quietly through the constellations. It won't stay. It never meant to. But for a little while, our sun warms an exile from another sky, and in that warmth, the exile speaks. It tells us that planetary systems don't end at their edges. They shed pieces, they trade materials, they send each other notes in the language of ice and dust. If you listen closely as 3i Atlas passes, you can almost hear the message. The galaxy is a conversation, and tonight, a voice from far away is speaking in our direction. Start with a picture. A young star wearing a wide, faint halo of gas and dust, the kind of disk where pebbles flow like a slow river, and everything is almost but not quite ready to become something larger. Into this delicate place drifts a wanderer like 3i Atlas. It doesn't need to be big or special, it just needs to be different, moving on a path and at a speed the local material isn't expecting. The planet maker idea is that such a passerby can tip a marginal environment over a threshold. A disk filled with grains that won't quite stick suddenly finds itself with new ingredients, new pressure ripples, new places where solids pile up instead of drifting away, and those changes can set off chain reactions that end many orbits later with planetesimals, the kilometre-scale seeds of planets. There are a few ways that can happen, and none require magic. The first is simply delivery. Interstellar objects are time capsules from other systems' building yards. If one passes through a dusty disk, it can shed material. Gas drives off ices, outgassing lifts dust, and small fragments can spool from its crust as it warms, cracks, or collides with local debris. Even a thin dusting matters. Icy grains carry sticky mantles that make collisions gentler and more likely to end in mergers instead of rebounds. Exotic organics, think tar-like tholins cooked under alien starlight, can act as glue at the right temperatures. Trace metals and mineral quirks alter how grains radiate heat and interact with gas, which changes where they settle. A gram here, a gram there, spread across a swathe of disk, can subtly tune the physics of sticking and settling in ways that add up. The second path is mechanical, gravity and motion doing their quiet work. A body slicing through gas creates a wake, like a boat through water. In a protoplanetary disk, that wake can be a pressure dent followed by a pressure bump. Dust is irresistibly drawn to pressure bumps because gas inside them orbits a hair closer to the true Keplerian speed. The headwind that normally robs pebbles of angular momentum weakens, and solids stop drifting inwards so fast. Collect enough pebbles in a bump, and you raise the local solids to gas ratio. Cross a critical threshold in a well-studied process, the streaming instability switches on. In that regime, drag forces between gas and tightly coupled pebbles create filaments and clumps of solids dense enough to collapse under their own gravity. What was a uniform drizzle of millimetre to centimetre grains becomes a patchwork of overdense streams. Those streams fragment into bound clods. Clods compact into planetesimals. The interstellar visitor didn't build a planet by itself. It carved a small harbour where the disk's own physics could do so more efficiently. The third path is thermal and chemical. As a volatile-rich body warms, its outgassing pumps CO, CO2, H2O, and other molecules into the surrounding gas. That does three things at once. It changes local cooling rates. Molecules radiate heat efficiently. It changes the mean molecular weight, and therefore the sound speed, of the gas, and it alters the sticking behaviour of nearby grains by frosting them with fresh ice. Even a faint temporary enrichment can shift a nearby snow line, the boundary where a species transitions from vapour to ice, by a small but meaningful amount. Near snow lines, grains undergo sintering. Think of frost welding, which strengthens contacts and helps aggregates survive collisions that would otherwise fragment them. If the visitor lingers or returns material along its path, it can leave behind a ribbon of enhanced stickiness, a corridor where pebbles grow faster and survive longer. Now add electricity and magnetism to the picture, because disks are not perfectly quiet. The sun's far-off UV, cosmic rays and local heating ionize a trickle of gas, which couples to magnetic fields. Turbulence rises and falls depending on how well ionized the gas is, magnetorotational instability in the high ionization patches, calmer dead zones elsewhere. A comet-like visitor that vents alkali vapours and dust can slightly increase ionization downstream. Metal atoms are easy to ionize, lighting up a patch of turbulence that didn't exist a few hours before. Paradoxically, this can be good for planetesimal birth. Turbulence concentrates particles in eddies and pressure maxima, creating pockets of extreme dust density. If the visitor is large enough to drive a weak bow shock, it can also thermally process grains, melting silicates into glassy chondrules or baking organics, producing a population of pebbles with different aerodynamic properties, measured by their Stokes number, which helps sort and concentrate them. There's also the blunt instrument of collisions. The disk is full of drifting pebbles and meter-scale boulders that struggle to grow because they either bounce off each other or drift inward and vanish before doubling in size. The notorious meter-size barrier. A fast intruder increases the local collision rate by stirring velocities. Too much stirring shatters things, but mild stirring plus a supply of sticky ice grains can move the system into a lucky growth regime. Some aggregates hit the right series of gentle impacts to cross the barrier, grow to decimeter and meter sizes, and then switch on pebble accretion. Once an object reaches a few kilometers across, it can gobble pebbles from the headwind efficiently. Growth becomes runaway. The seed matters, but the disk does the heavy lifting after that. Capture is another subtle possibility. Most interstellar objects will not be caught. Their hyperbolic speed is simply too high. But in a dense gas-rich disk, drag can be a brake. If the visitor threads a long path through gas, it loses a sliver of kinetic energy. Very rarely that sliver is enough to transform a flyby into a loose, temporary orbit. Even a temporary capture that lasts a few hundred orbits is a gift. The object repeatedly ploughs the same annulus, seeding and reseeding, carving a persistent pressure pattern and shedding material at each periapsis. On departure, it leaves behind a ring more crowded with pebbles than before, prime real estate for streaming instability to ignite. Zoom into the grain scale for a moment, because planet making lives there. Grains carry a history in their surfaces: roughness, porosity, frost, and thin films of organics. New dust from a visitor tends to be fluffy and porous, excellent for dissipating impact energy. Porous aggregates stick at higher collision speeds than compact ones. Coat local refractory grains with a whisper of fresh ice, and you raise their sticking threshold again. Each tweak widens the window where hit and stick beats hit and bounce. In a disk that was stuck at the wrong side of that boundary, a small chemical nudge can unjam growth. The planet maker idea also extends to composition. Worlds inherit the flavours of the pebbles that built them. If a wanderer brings in carbon-rich dust to a carbon-poor region, the next generation of planetesimals will trap more organics. If it sprinkles sodium or potassium that alter melting points, later heating events, shocks, lightning, close passes to the star process those pebbles differently. Over millions of years, those tiny biases can decide which embryos retain water, which crusts form basalts versus more exotic lavas, which atmospheres start off thick or thin. A visitor's cargo is not just mass, it's destiny in powder form. You might wonder whether all this is too gentle to matter. After all, a single object is tiny compared to a disk. The key is thresholds. Many disk processes are non-linear. Nothing happens, and then, once a ratio or speed or density crosses a tipping point, everything happens at once. A 10 to 20% boost in local solids, a modest flattening of a pressure gradient, a slight shift in the snow line. These are the kinds of nudges that flip the switch on streaming instability or make pebble accretion efficient. The visitor doesn't have to sculpt a planet, it just has to nudge the environment from almost to now. There's a time element too. Disks evolve quickly by cosmic standards. Gas begins to clear in a few million years. Pebbles drift inward on 100 to 1,000-year timescales. That means opportunities are fleeting. If the visitor arrives while the disk is still rich in gas and the pebbles are mid-migration, the payoff is large. Arrive too late, and there isn't enough material left to amplify. That's why the notion feels exciting. The galaxy sends countless small messengers on random paths. When one of them threads the needle, right place, right speed, right disk age, the encounter can leave an outsized fingerprint. Even outside young disks, echoes of the idea remain. In a mature system like ours, a passerby can still alter destinies by delivering volatiles to dry worlds, tweaking resonances in asteroid belts, or stirring outer reservoirs so that comets rain inward for a while. Those are not planet birth events, but they are planet-shaping events. Oceans filled, atmospheres replenished, climates nudged. The same physics, delivery, pressure structures, mild stirring operates. The outcomes just shift from create to remodel. In the end, calling an interstellar visitor a planet maker is shorthand for a bundle of small physical assists. A bit of dust that sticks better, a pressure bump that holds pebbles longer, a sliver of gas that cools faster or ionizes more easily, a gentle increase in collisions that favours growth over destruction. Put those assists into a disk that's already poised on the edge of structure, and you don't need a miracle. You need a passerby with good timing. Whether 3i Atlas is such a passerby is an observational question, one we can approach by watching how similar bodies behave, by modelling wakes and outgassing in realistic disks, and by staying open to the idea that in a galaxy full of near misses, some misses matter. If you could hold a pinch of 3i Atlas in your hand, just a thimble of its stuff, you'd be holding a layered history of the galaxy. At the coarsest level, it's a blend of rock, ice, and carbon-rich material, but each of those words hides entire worlds of detail. The rocky fraction is not a single stone, so much as a mixture of silicate minerals and metals, tiny crystals of olivine and pyroxene, flecks of iron-nickel, glassy shards born from rapid heating and cooling, and sulfides like troilite that formed in warm, reducing pockets. Some grains are crystalline, with neat atomic lattices that tell of slow, deliberate growth near a young star. Others are amorphous, frozen chaos that whispers of fast cooling in the cold between the stars. Mixed among them are GEMS, glass with embedded metal and sulfides, the kind of exotic textures we find in cometary dust caught by high-altitude aircraft, and in samples returned by missions like Stardust. They look like dark sugar under the microscope, but they record temperature, pressure, and chemistry across distances no laboratory could recreate. The ice is not just water. Water is the backbone, yes, but frozen into and around it are other volatiles that turn a passive snowball into an active comet. Carbon monoxide and carbon dioxide that flash to vapour far from the sun, methane and ammonia that wake up a bit closer in, methanol and formaldehyde that ride along as both ice and gas depending on subtle changes in temperature. These ices matter because they are both propellant and paintbrush. When warmed, they vent outward, dragging dust into the coma. When cold, they coat grains with frost that changes everything about how those grains collide. A grain with a thin film of water ice can stick at speeds that would make a bare mineral bounce or shatter. Layer by layer, the frozen shells act like shock absorbers, raising the odds that two drifting particles merge instead of ricochet. In the life of a disk, that tiny advantage matters. The carbon-rich material is where things get delightfully messy. Under ultraviolet light and cosmic rays, simple carbon-bearing molecules rearrange themselves into complex tar-like organics called tholins, reddish sticky films that build up on ice and dust. Sprinkle in polycyclic aromatic hydrocarbons, long-chain hydrocarbons, nitriles, and oxygen-bearing organics, and you have a chemistry set on a grain. Some of these compounds are fragile, some are robust, some carry functional groups that make them great adhesives at low temperatures, some are reactive precursors for more intricate molecules. Spacecraft have sniffed amino acid precursors and even simple amino acids in comet comae. Meteorites carry sugars, nucleobase relatives, and a zoo of prebiotic molecules. None of this makes a comet alive, but it does make it an effective delivery system for the ingredients of complexity. Zoom in even further, and those ingredients become a structure problem. Dust in comets isn't usually a pile of smooth spheres. It's a fractal fluff, aggregates built from smaller aggregates. Think of it like a snowball of dandelion seeds, extremely porous, full of voids, able to soak up energy during a collision. Porosity helps grains stick, but it also changes how they move through gas, how quickly they spiral inward, which pressure ridges can trap them, how they align with magnetic eddies. The iron and sulfide specks inside those aggregates change their optical properties and thermal response. A grain that cools efficiently at night grows thicker frost and thus becomes even stickier the next day. What looks like just dust in a photograph is in truth a living microphysics factory, where every composition tweak nudges the probability of growth. The mixture isn't uniform from core to crust. Deep inside, ices may be more amorphous, glass-like water that can trap gases in its structure. Warm it slightly, and that amorphous ice crystallizes, releasing its captives in a sudden breath. Such phase changes can drive outbursts, brief flares of activity that lift new material off the surface and expose fresher, more volatile rich layers beneath. Near the surface, solar processing darkens and hardens organics, sintering grains into fragile crust that can crack, collapse and slump as gas pressure builds below. Every collapse reshapes the surface, creating pits, terraces and jets. Each jet is a conveyor belt spraying a new cocktail of dust and gas into space, where sunlight and radiation cook it into yet more complex organics, before some of it reaccumulates as a soft mantle. Chemistry tracks its origins with isotopic tags. Ratios like D/H in water, 13C/12C in organics, or 15 N enrichments in nitriles act like return addresses. Some values scream formed in the deep freeze, others whisper of warmer kitchens. A body like 3I Atlas, born under another sun, could carry ratios that don't line up with anything common in our own comet families, or it could overlap, suggesting a kind of convergent chemistry across star systems. Either way, those numbers matter because they connect composition to environment, how much ultraviolet flooded the nursery, how fast grains grew, how far they wandered before being locked into an embryo that was later kicked out into interstellar exile. Even metals have roles beyond ballast. Nanophase iron grains embedded in glass can heat rapidly under sunlight, driving micro-outgassing and creating rocket forces on dust that help loft it. Metal atoms and simple metal-bearing molecules change the ionization balance in the surrounding gas. That tweaks the coupling to magnetic fields and the spectrum of turbulence. Turbulence, in turn, is a sorting machine, segregating particles by size and stopping power, sweeping like a sieve that keeps some pebbles and lets others pass. A slightly more ionized patch can form eddies that concentrate centimetre-scale pebbles by factors of 100. Exactly the kind of enhancement that flips a region into planetesimal making mode. The inventory also carries heat stories. Some silicates show that they were once melted. Chondrule-like textures with signatures of fleeting high-temperature events. You get those from shocks, lightning or close brushes with hot regions. Mixed with them are ultra-refractory grains that must have condensed in intense heat before being flung outward, and ultra-cold condensates that formed where temperatures never rose above tens of kelvins. To assemble both extremes in one handful of dust requires motion, radial mixing in a disk, turbulent lofting above and back down into the mid-plane, or capture of foreign material along the way. An interstellar object is, by definition, a migrant. Its rock draw is likely a sampler platter of many neighbourhoods. Water deserves its own pause because it is both the simplest ice and the most influential. Frosted onto silicates, it acts as glue. Frozen into pores, it acts as a structural scaffold. Sublimating, it acts as a piston pushing dust outward. Refreezing in shade, it can cement debris into crust. The line in a disk where water flips from vapour to ice, the snow line, is a cradle for growth because the same mass of solids suddenly includes a lot more material when water is solid. If a traveller like 3I Atlas carries abundant water ice, plus a bouquet of other volatiles, it can locally thicken the population of sticky grains right where sticking is already favoured. Even after the visitor leaves, that thickened zone can persist, a kind of breadcrumb trail of enhanced solids drifting together toward a future world. Organic films don't just help grains stick, they shape planets' personalities later. Carbon-rich pebbles build darker, lower albedo surfaces that absorb sunlight differently. They outgas molecules that can seed primordial atmospheres. They alter the redox state of crustal rocks as they melt and differentiate. A slight excess of organics in the feedstock of a forming moon or planet can decide whether lakes of hydrocarbons survive at the surface, whether an early atmosphere can hold on to methane, whether hazes form that cool a young world or warm it through greenhouse absorption. In that light, the cosmic breadcrumbs are not only clues for astronomers, but also recipes that worlds will follow. Then there's sulfur, a quiet player with loud consequences. Sulfides like iron sulfide and volatile sulfur compounds such as hydrogen sulfide and sulfur dioxide are abundant in cometary comae. Sulfur changes melting points, influences metal segregation in cores, and adds complexity to surface chemistry. On grains, sulfur-bearing ices can polymerize into rubbery films that further raise sticking thresholds. On worlds, sulfur gases sculpt climates and interact with sunlight, sometimes building reflective hazes. A visitor with a sulfur-rich mix leaves different fingerprints than one dominated by simpler CHO chemistry. All of these ingredients ride in specific sizes. The coma contains fine submicron dust that scatters blue light, larger micron to millimeter grains that redden the glow, and occasional chunks big enough to tumble as discrete specks in images. Size decides aerodynamics. Aerodynamics decides fate. Millimeter pebbles, with Stokes numbers near the sweet spot, are the currency of pebble accretion. Meter boulders are the victims of the drift barrier. If 3i Atlas vents a size distribution skewed toward pebbles, it is not just shedding mass, it is minting the coins of planet growth and tossing them into whatever bank the surrounding environment provides. Underneath the catalogue of compounds and grains is a simple pattern. The same materials that make 3i Atlas active and beautiful also make it useful to a disk trying to build planets. Ices enable stickiness and gas release. Refractory dust gives mass and scaffolding. Organics act as glue and future atmosphere feedstock. Metals and sulfides tune heat, charge, and structure. Each jet is a chemistry lesson. Each falling snow of dust is a local physics experiment. When astronomers call these bits breadcrumbs, they mean that following their composition leads us back to formation conditions and forward to likely outcomes. The trail is not linear. It loops through cold molecular clouds, warm inner disks, shock fronts, and quiet outskirts, before settling into a nucleus that may spend eons in the dark, only to flare into relevance in a brief brush with sunlight near some future star. So imagine 3i Atlas exhaling as it passes. A whisper of water, a breath of carbon monoxide, a confetti of silicate fluff coated in reddish organics. Each particle drifts, sticks, or sublimes according to rules written in its composition. Each carries a memory of temperatures survived, lights endured, neighbours met. Together, they are more than debris. They're the smallest units of a big story, the parts list for worlds that do not yet exist. And if even a fraction of that cloud finds its way into a hospitable eddy or a waiting pressure ridge, the story continues. Dust to pebble, pebble to planetesimal, planetesimal to the quiet roundness of a newborn world. Picture a calm disk of gas and dust circling a young star, a nearly flat river of particles moving in orderly lanes. Into this river slips a visitor like 3i Atlas. It is small compared to a planet and fleeting compared to the age of a system, yet gravity does not care about stature. Even a modest mass moving through a sea of pebbles and gas draws a response. The first sign is a soft focusing of trajectories. Grains that would have missed now veer inward by a few degrees, guided by the visitor's pull. Most still miss, but they pass closer than they would have, and that closeness subtly thickens the stream behind it. In 3 dimensions, you can imagine a narrow invisible funnel forming upstream and a faint overdense plume downstream, a wake. Like ripples on a pond, the wake falls away with distance, but while it lasts, it is a place where solids gently slow, meet more often, and stick more easily. Gravity's hand is gentle here because everything is cushioned by gas. Dust and pebbles don't move freely. They feel drag. Drag is the mediator between the visitor's pull and the disk's response, As 3i Atlas tugs a pebble off its perfect circular path, gas resists the deviation, bleeding off the pebble's relative speed. That braking converts a wild deflection into a settled one, leaving the pebble on a slightly different orbit, perhaps a hair closer to the star, perhaps a hair farther out, but crucially closer to many other pebbles that were tugged in a similar way. In a purely gravitational ballet with no gas, close encounters would fling particles away as often as they gather them. In a gas-rich disk, drag turns temporary crowding into semi-permanent structure. Follow 3i Atlas for a moment as it ploughs through the midplane. Upstream, pebbles begin to sense its pull and drift into converging streams. At closest approach, some are deflected enough to cross paths with others caught on the opposite side. Relative speeds that were once whisper quiet become just energetic enough to shake loose frost, squish porous aggregates flatter, and create larger, stickier contact patches. Downstream, the pebbles settle into a narrow sheet where their orbits line up more closely than before. That sheet is not a solid, but its density is measurably higher, and in the economics of planet formation, density is capital. Interest accrues fastest where the capital is thickest. Now scale up from pebbles to the gas itself. A body sliding through gas produces a bow wave in front and a low-pressure pocket behind. The gas tries to flow around the intruder, speeding up along the flanks and falling into a slow eddy in its lee. Dust is enslaved to these pressure patterns because dust wants to move at the local gas speed. Where pressure is high, gas orbits slightly faster relative to solids, and where pressure is low, it orbits slightly slower. The net result is a pair of pressure features, one in front, one behind, that shepherd dust into lanes. Even after the visitor has moved on, those lanes can persist for many orbital periods, because the disk is viscous only in the slower sense. Think of cart tracks on a dirt road. One pass can leave grooves that focus later traffic. From lanes, we get bumps. A pressure bump is a special place where the usual inward drift of pebbles stalls. In most of a disk, gas orbits a little slower than Keplerian because pressure supports some of its weight. Pebbles feel a headwind, lose angular momentum and drift inward. At a bump, the local pressure gradient flattens or reverses, cancelling the headwind. Pebbles pile up. If the wake of 3i Atlas leaves even a modest bump in its trail, the disk takes over from there. More pebbles arrive from far away and stop at the bump. The solids to gas ratio rises. Feedback between drag and solids. Concentration strengthens. Streaming instability flickers on. Gravity no longer needs the visitor's mass to lead. The collective self-gravity of the pebble cloud becomes the star of the scene, causing strands to fragment into bound clumps, planetesimals in embryo. All the while, the visitor's own gravity is writing small scripts in the orbits it touches. Consider a pebble's local motion as a little epicycle, a tiny oval added to its big orbit, nudged by the passing mass. Those epicycles do not line up randomly. Behind the intruder, they tend to align, creating corridors where relative velocities are low. Low speeds favour sticking. Ahead of the intruder, the opposite is true. Some corridors see mild speed-ups, which can be destructive. But even destruction has a role, grinding fragile aggregates into a fog of sub-millimeter grains that are wonderfully sticky when they collide with something just a bit larger. Gravity doesn't choose winners, it supplies variance. Drag and material physics decide which patches turn that variance into growth. If the visitor passes near a juvenile planet, the kind of 100 to 1,000 kilometer body that already owns a small gravitational domain, we get a second layer of structure. The hill sphere of the juvenile becomes a net, catching pebbles whose paths were only slightly altered by the visitor. Those pebbles would have slipped past otherwise. Now they are slowed just enough to fall into temporary orbits around the juvenile and spiral down through gas drag. Pebble accretion turned on by a third party. The intruder does not feed the seed directly. It bumps the buffet table so that more food lands in reach. Resonances can be tickled too. Every ring in a disk has natural frequencies at which orbits exchange energy efficiently with a perturbation. A quick flyby is more like a tap than a steady push, but if that tap lines up with one of the local frequencies, say near where a pressure ridge is already marginally stable, it can amplify a pattern. A faint spiral density wave can strengthen. A weak eccentricity in a ring can grow. A barely there gap can deepen into a real filter for pebbles. Once a pattern crosses a threshold, the disk's self-consistent physics keeps it alive long after the tap itself is gone. There is also the quiet effect of dynamical friction, counterintuitive at first, but potent over time. As 3i Atlas moves through a sea of smaller bodies, it feels a drag force from the wake of material it perturbs. That drag slightly slows and deflects the visitor, but more importantly it cools the random motions of the sea around it. In a statistical sense, energies are exchanged so that the swarm becomes a touch more orderly. In a gas disk, gas drag dominates, but dynamical friction still hums in the background for the solid component, constantly trying to reduce the dispersion of velocities. Lower dispersion means gentler collisions, and gentler collisions are the currency of growth. Consider vertical structure. Disks are thin, but not infinitely so. Dust settles toward the midplane under gravity and is stirred upward by turbulence. A passing mass can press on that vertical balance, briefly compressing the layer beneath it and lofting a faint plume at its edges, like a hand passing over tall grass. Compression boosts midplane density where sticking is best. Lofted plumes give fresh, frost-coated grains a chance to cool and then rain back down, stickier than before. The net is a mid-plane that is not only denser, but also stratified by composition, with ice-rich aggregates concentrated in the sweet zone for fast growth. Not every effect is immediately constructive. Slightly faster relative speeds in some regions will fragment aggregates. But fragmentation is not the end, it's recycling. The fragments have more surface area per unit mass, better radiative cooling, and often thicker ice mantles per mass. They stick readily to survivors. In the presence of a pressure bump, even a population battered by a brief speed-up will repopulate the mass spectrum at the pebble sizes that drive runaway pebble accretion. Gravity's gentle hand may ruffle the disk, but the disk's chemistry and aerodynamics turn ruffles into texture. Time matters. The visitor's wake is strongest immediately, then fades, yet the structures it excites can outlive it. Pebbles that were parked in a bump will linger for hundreds to thousands of orbits. If streaming instability ignites, the resulting planetesimals are permanent. If a spiral is amplified, its torque on the surrounding gas can continue to sculpt rings. In this way, a minute of gravitational attention can become a million-year architectural feature. The disk is a memory medium. Gravity writes to it in faint lines that gas viscosity and pebble drift only slowly erase. Even the visitor's own outgassing couples to gravity. Jets impart tiny thrust that jitter its path, creating small variations in where and how strongly it tugs on nearby material. Those jitters spread structure over a broader swath than a clean, smooth passage would. Instead of a single, narrow wake, you get a braided ribbon of slightly offset lanes, each an invitation for solids to congregate. The cumulative effect is a widened corridor of opportunity rather than a single sharp ridge. Imagine now the encounter from the perspective of a single pebble. It begins in a nearly circular path at the disk's mid-plane. Gas gives it a headwind, so it drifts inward at sedate pace. Far upstream, the pebble enters a region where orbits are just slightly out of tune. Tiny gravitational tugs add a centimetre per second here. Subtract a centimetre per second there. Its epicycle grows. Its path crosses others' paths a bit more often. It grazes a few aggregates, exchanging a smear of frost, absorbing the minor impacts without falling apart. Then the visitor passes. The pebble is deflected by a fraction of a degree, enough to place it into a pressure shelf where the headwind drops. its inward drift slows to almost nothing. Other pebbles, similarly treated, begin to surround it. Gas drag bleeds away the last relative motions until the cluster is a soft, crowded place. Feedback between gas and solids strengthens, filaments blossom, and our pebble suddenly finds itself in a collapsing thread of material. Within a few orbits, the thread fragments. Within a few years, a kilometre-scale body exists where there was once only drizzle. No miracle, just a sequence of small, consistent nudges culminating in self-gravity taking the stage. If a juvenile planet is nearby, the story tilts again. Pebbles captured into its hill sphere feel two competing pulls, the planet's gravity and the stars. Gas drag damps their chaotic paths, allowing them to spiral toward the planet rather than slingshot away. The capture cross-section, the effective net size for pebbles, depends on relative speed and drag. A visitor that has pre-sorted pebbles into a particular size range, the sweet spot where drag is strongest, and lowered their random speeds makes that net much bigger. The planet grows faster for a while, not because it met the visitor, but because the visitor prepared its meal. None of this demands a massive intruder. The equations scale beautifully. A larger body writes deeper, longer-lived wakes. A smaller one writes shallower, shorter notes. Many small passes over the life of a disk can layer their effects like sediment. Each one faint on its own, together decisive. The galaxy supplies statistics. Objects like 3i Atlas are rare in our experience only because we have just started watching carefully. In cosmic terms, they are likely common, and their cumulative handwriting may be all over young systems. So gravity's gentle hand is not a single push, but an ensemble of touches, focusing that thickens streams, wakes that sculpt pressure, bumps that cancel headwinds, epicycles that align corridors, vertical compressions that fatten the midplane, captures that feed growing seeds, resonant taps that amplify patterns, and a patient background of drag-turning chaos into order. The romance of a planet maker is simply the poetry we use to talk about thresholds. A disk is a poised instrument. It will play a symphony if anything bows the strings just right. A passing wanderer doesn't compose the music. It draws the bow for a bar or two, and then the instrument rings on by itself. Begin with a single grain, a fleck of silicate, a whisper of ice, wrapped in a thin film of organics. It drifts in the gas like dust in a sunbeam, carried by eddies, nudged by pressure, quietly trading partners in slow-motion dances. Two such flecks tap together, and because their surfaces are rough and a little sticky at these temperatures, they hold. Not with the strength of rock, but with the tenderness of frost. Tap becomes cluster. Cluster becomes a feathery flake. And soon we're not dealing with spheres at all but fractal snow. Porous, lacy aggregates with the strength of meringue and the heft of a sigh. This early growth is the kingdom of gentle collisions. In the outer, cold disk where ice mantles abound, grains can stick up to relative speeds of tens of centimetres per second, sometimes even a bit more, because frost acts like a shock absorber. In the warm inner disk, bare silicates are fussier. Bump them much above a few centimetres per second and they'll bounce or chip. Porosity helps. Fluffy aggregates deform, dissipate energy, and present big cross-sections to one another. With every merger, the structure changes. Voids fill, filaments compress, contacts sinter. The same aggregate that was airy and delicate at a millimetre becomes surprisingly sturdy at a centimetre, simply because the internal web has more places to distribute stress. Then a new rhythm enters, gas drag and radial drift. Gas in a protoplanetary disk orbits a hair slower than perfect Keplerian speed, because pressure partly supports its weight. Solids don't feel pressure, they feel gravity alone and want to orbit slightly faster. The mismatch creates a headwind on pebbles. Small grains, so tightly coupled to gas that they're almost smoke, hardly notice. But as aggregates grow toward millimetres and centimetres, they decouple just enough to feel that headwind biting. The result is inward drift. Pebbles slowly spiral toward the star, losing angular momentum grain by grain. Sizes that feel the headwind most strongly, often with gas coupling measured by a dimensionless Stokes number around 0.01 to 1, drift fastest. In the inner disk, that can mean peril. You grow, you drift, you're gone. This is the notorious drift barrier, and it is joined by two siblings, the bouncing barrier and the fragmentation barrier. At intermediate sizes, many collisions no longer end in embraces, but in polite rebounds that halt growth. Push the relative speed a bit higher and aggregates chip or shatter, replenishing small dust but eating the gains. For years, these barriers seem to draw a hard line under pebbles, as if nature were saying this far, no farther. Nature, though, loves thresholds that flip when conditions nudge just right. Enter concentration. Gas is not smooth. It harbours eddies, vortices, and pressure bumps. Pebbles feel these structures as tailwinds and calm bays. In a pressure bump, the usual headwind weakens or reverses. Pebbles stop drifting inward and begin to collect. Turbulent eddies, especially those whose turnover times match a pebble's response to drag, herd particles into filaments and clumps. Even without any glue, you can create local pockets where the solids to gas ratio, call it Z, rises from a background of a few percent to something much higher. Now the key. When Z crosses a modest, very achievable threshold in a region where pebbles have the right aerodynamic sweet spot, Stokes numbers of about 0.01 to 0.3 depending on conditions, a feedback loop ignites. Pebbles tug on gas just as gas tugs on pebbles. In a dense stream, their collective drag slows the local gas toward the pebble's speed, reducing the headwind that would otherwise flush them away. Slower headwind means less drift. Less drift means more time to pile up. More pile-up strengthens the drag-back effect. The phenomenon is called the streaming instability, and it turns a smooth drizzle of pebbles into braided rivers of solids. Within those rivers, self-gravity wakes up. Imagine a long, slightly overdense filament of pebbles. Tiny fluctuations make some sections denser than others. Where density peaks, gravity begins to hold hands with drag. Gas drag damps random motions, cooling the pebble cloud. Gravity amplifies the densest knots. Pebble filaments bead up like dew on a spiderweb, each bead collapsing into a bound many-kilometre body, a planetesimal, in a geologic blink. No need for a single, lucky boulder to dodge every barrier. The collective turns the barriers sideways, turning drift into delivery and collisions into compaction rather than demolition. The newborn planesimals are not marble-smooth spheres. They're rubble-pile hearts with strength set by gravity and friction, sometimes laced with ices that later become plumbing for comets. Their sizes form a characteristic spectrum, many tens of kilometres objects, a tail to hundreds, and fewer small ones than you might guess. Because once collapse begins, it tends to leapfrog the meter-sized graveyard entirely. This is the great shortcut. The streaming instability bypasses the slow, failure-prone step of building a single object through billions of two-body merges. It lets the disk perform a group act. None of this erases the role of collision physics. It reframes it. Before the instability, collisions set the material properties that determine which sizes couple best to gas. Porosity, stickiness, ice content, the balance of fluffy versus compact pebbles. During the instability, collisions within a collapsing clump dissipate energy and help the clump stay bound. After collapse, collisions among planetesimals, now high stakes, gravitationally focused impacts begin the next phase, accretion through mergers and cratering, guided by the seeds the instability made. The environment decides where this machine runs best. Near snow lines, those radial bands where a particular volatile flips from vapour to ice, pebble surfaces change character. Icy mantles thicken, sticking thresholds rise, particle sizes that achieve the sweet spot for coupling become abundant. Add a gentle pressure bump at the snow line, common because changes in opacity and chemistry alter gas structure, and you've built a natural trap. Pebbles drift inward from colder regions, park at the bump, and crank Z upward until the streaming instability clicks on. It's no accident that many models find rings and gaps in young disks near expected snow lines. The physics practically begs for them. Vertical structure helps too. Dust settles toward the mid-plane under gravity, while turbulence tries to stir it up. If turbulence is mild, a thin, dense mid-plane layer forms, perfect for pushing Z over the edge. If turbulence is strong, particles stay lofted, which can delay or diffuse concentration, but turbulence is a double-edged sword. It also generates the very eddies and pressure fluctuations that cluster pebbles horizontally. In practice, disks often live in the sweet tension between too quiet and too loud, where settling and stirring conspire to concentrate solids just enough. What about composition? It matters intimately. Ice-rich pebbles are stickier and can grow larger at lower internal densities, achieving Stokes numbers that the instability loves without becoming heavy, cannonballs that fragment on impact. Carbonaceous coatings, tholins, organics, act like glues at low temperatures. Metal grains tweak ionization and cooling, which tunes turbulence. Sulfur-bearing compounds soften or strengthen aggregates in subtle ways. Even thermal history, where the pebbles carry glassy chondrule-like bits from shock heating, alters aerodynamics. The streaming pathway is democratic about ingredients, but it is sensitive to how those ingredients set the aerodynamic dial. Scale the lens back out and you see a choreography of thresholds. Pebble growth, by sticking until bouncing threatens. Drift into traps until Z crosses a line. Filaments bloom until gravity catches. Collapse races until planetesimals emerge. Each stage poses a barrier and offers a detour. A passing pressure bump here, a snow line there, a transient wake from a visitor threading the disk. The system is littered with opportunities to nudge conditions over the necessary edges. That's why the journey from pebbles to planetesimals can be fast once it starts. A region can spend a long time, almost ready, then switch states in a few local orbits, leaving behind a new population of seeds that reshape everything downstream. Once seeds exist, a new engine roars to life. Pebble accretion. Pebbles drifting inward feel a headwind. Seeds feel it too, but their gravity bends pebble paths. In gas, a pebble that would have blown past a seed in vacuum instead loses just enough energy to be captured, spiraling down to join the seed. This is not the slow, hit-or-miss capture of dry rock in space. It's a damped, guided rain. The efficiency is astonishing. A 100-kilometre seed can sweep up pebbles from a cross-section far bigger than itself, limited mainly by its hill sphere, its zone of dominance, over gas-damped pebbles, and by how long the pebble flux lasts. In this regime, growth accelerates. Bigger seeds capture more pebbles faster, creating a runaway spread in sizes. Embryos emerge, then cores, then, if gas is still around and the core grows quickly enough, giant planets. Even where gas has thinned, the legacy of streaming and pebble accretion persists. Leftover pebbles can be reworked into rings. Planetesimals can be herded by forming planets into belts and resonances. Collisional families can seed future dust that keeps disks glowing in scattered light for millions of years. The initial conditions stamped by the pebbles to planetesimals transition, how many seeds, how big, how clustered, echo through the architecture of the final system, whether it favours a few giant cores, a crowd of super-Earths, or a sparse scattering of survivors. And always, the microphysics whispers through the grandeur. Every time two aggregates meet, their surfaces decide the outcome. Roughness grips or slides, frost cushions or splinters, organics glue or smear. Every time pebbles enter a pressure bump, aerodynamics decides whether they hover or leak through. Every time filaments form, gas drag decides whether they cool into beads or disperse. The streaming instability is a grand name for a humble truth. Solids and gas talk to each other. When there are enough solids in the right sizes, their collective voice is loud enough to change the gas itself, and that change cradles the birth of planetesimals. So the road from dust to worlds is not a straight climb, but a sequence of plateaus and sudden staircases. You wander the flatlands of gentle stick-in until the paths converge. You reach a balcony where drift focuses traffic. Then, all at once, gravity opens a hidden door and the room changes shape. By the time the lights steady again, a new thing exists. Not a pebble, not a boulder, but a body with its own horizon. A place with up and down, with inside and outside. Give a disk enough chances to reach those thresholds, and it will fill itself with such places. Give one of those places time, heat, and chemistry, and it might someday wear an ocean, brew a sky, and listen to rain. The ladder between the flake and the future is built from thresholds crossed together. And the beauty is that once the disk learns the tune, once pebbles start to sing with the gas, worlds begin to hum into being almost as a matter of course. Begin with two ghosts moving in different ways through our memories. One a riddle with no visible tail, the other a classic comet from somewhere else. From these opposites, Oumuamua, one eye, and Borisov, two eye, we learned what interstellar visitors can be and how easily our expectations can be wrong. The first lesson was about surprise itself. Oumuamua arrived like a sliver in the sunlight, faint, fast, and already leaving when we found it. No coma, no tail, only a changing brightness that suggested either a very elongated or very flattened body tumbling end over end. Its path was hyperbolic, proving it was unbound, and its motion showed a small but real non-gravitational acceleration. That single clue detonated 1,000 hypotheses. Outgassing of an unusual volatile we failed to see, hydrogen released from irradiated ice, nitrogen flakes chipped off a Pluto-like world, even radiation pressure acting on an extremely low-density fractal aggregate. The uncomfortable truth underneath the headlines was methodological. When discovery comes late and data are sparse, many models can fit the same meagre points. The scientific posture that followed, embrace uncertainty, lodge multiple working hypotheses, look for tests that discriminate fast, became the template for how to treat any future interstellar oddball. Borisov, by contrast, behaved like it had stepped out of a textbook. It grew a coma and tail. Its spectrum showed familiar cometary gases. Dust streamed, jets flickered, and later it even fragmented, drama we know from long-period comets born in our own deep freeze. That normalcy was profound. It told us that at least some other planetary systems grow the same kind of ice-rich leftovers ours does. It also gave us a calibration. Coma brightness versus dust production, gas ratios versus temperature history, colour slopes versus organics. Where Oumuamua taught humility about exotic possibilities, Borisov anchored our expectations with a reference case. Detection bias was the next hard-earned lesson. We spotted Oumuamua only after perihelion, when it was already fading. Borisov, still not early enough to throw everything at it in time. Both encounters revealed how much we miss simply because our surveys aren't fast or deep enough in the right patches of sky, at the right cadence. That led to practical conclusions. We need wider, deeper, faster surveys, automated flagging for hyperbolic motion, and a global ready-set-go network for follow-up photometry and spectroscopy the instant a candidate pops. It also reframed what rare means. 2 detections in quick succession suggested interstellar objects are not unicorns. They were merely invisible to us until our telescopes and software matured. Planning for 3, I means assuming the sky is busier than our catalogues imply. We also learned how fragile interpretation can be when chemistry hides. Oumuamua's anomalous acceleration begged for outgassing, yet we didn't catch the usual gas signatures. That forced us to consider ices that sublimate quietly, or mechanisms that mimic outgassing without leaving a spectral fingerprint. The meta lesson is to decouple inferences. Dynamics can indicate a force. Spectra, or the lack thereof, put limits on which forces are plausible. Surface physics and geometry can conspire to hide activity even when it's present. Borisov, happily loud with gas, showed the flip side. When chemistry speaks, it can dominate the story, locking down formation temperatures, ice inventories, and the dust-to-gas balance. Geometry and rotation turned out to be cruel masters. Oumuamua's wild light curve amplitude reminded us that shape, spin state, and surface patchiness can fool simple models. A wafer, a cigar, a shattered sheet, a fluffy clump. Each geometry produces different thermal lags and outgassing patterns, leading to different thrust vectors and different brightness modulations. Lesson: never hang a firm conclusion on shape without independent constraints. Use light curves, thermal modelling, and non-gravitational acceleration together. Borisov's more sedate behaviour, plus a visible coma, let us apply classical comet techniques. AFV-RL, dust colours, grain sizes, highlighting how much easier it is to reason when nature gives you a tail. Origins enter the chat with both objects. Ejection mechanisms, scattering by growing giant planets, resonant kicks, even stellar flybys, came into focus as factory lines that can fling billions of small bodies into interstellar space over a system's lifetime. The plausibility of each mechanism depends on how common different planetary architectures are. If most systems build giant planets early, they may flood the galaxy with cometary debris. If compact super-Earth systems dominate, the mass budget and ejection efficiency look different. Oumuamua's oddities encouraged models involving tidal shredding or surface processing in harsh radiation fields. Borisov's normalcy favoured the ejected Oort cloud comet picture. The synthesis is that multiple channels likely operate, so the interstellar population is a mixture, and every new object is a sample from that mixture. Timescales and readiness were another takeaway. By the time the community coordinated on Oumuamua, the window for high-resolution spectroscopy and thermal IR had largely closed. Borisov gave us more time, and the quality gap between the two datasets was dramatic. The operational lesson is blunt. Treat every hyperbolic candidate as a once-per-decade event, even if more will come. Pre-allocate telescope time on triggers, keep observation scripts on the shelf, and empower rapid response pipelines that can fit orbits, predict visibility, and push alerts within hours. The earlier we characterize, the tighter our constraints on composition, size, and activity, and the narrower the corridor for wild theories to proliferate. We also learned how valuable multi-wavelength coverage is. Optical light curves constrain shape and rotation. Near-IR probes ices. Thermal IR nail size and albedo when the coma is absent. Radio can see specific molecules in emission. Polarimetry tells you about grain sizes and porosity. Ultraviolet catches photochemical products you miss elsewhere. Oumuamua dared us to do thermal and radio when we barely had time. Borisov rewarded teams that spread across the spectrum. For a future visitor like 3i Atlas, the lesson is to choreograph a panchromatic campaign from the jump, because each band answers a different question and closes a different loophole. On the theoretical side, Oumuamua taught restraint. Elegant mechanisms can be wrong if they require fine-tuning or predict populations we don't see. At the same time, it taught openness. Laboratory work on sublimation of exotic ices and numerical experiments on radiation pressure effects became more relevant than anyone predicted. Borisov reminded modelers that the boring answer, "it's a comet like ours," should always be the default null hypothesis, and that deviations from boring need clear, reproducible evidence. Compositionally, Borisov hinted that some interstellar comets may be unusually volatile rich, with strong CO seen far from the sun and dust that skewed towards small, possibly more pristine grains. That matters for the planet maker idea, because volatile-rich pebbles are stickier and more effective at changing local disk physics if they're injected into a young system. Oumuamua, odd as it was, kept the door open to a different cargo. Low density, possibly brittle material whose aerodynamic behaviour could be extreme. If that class exists in numbers, their interaction with gas, drag, radiation pressure, sublimation skins would be very different from compact comets. The pragmatic takeaway is to expect diversity in both mechanical and chemical properties, and to design observing strategies that can distinguish fluffy from compact, volatile rich from volatile poor quickly. Durability under solar heating was a split lesson. Borisov survived a while and then shed fragments, as many comets do. Oumuamua showed no obvious dust even as it accelerated slightly. One possibility is that some interstellar bodies carry crusts hardened by long exposure to cosmic rays and micrometeoroids, insulating interiors until heat penetrates deep enough to drive unusual outgassing. Another is that certain materials sublimate clean, leaving little detectable dust. Either way, the inference is operational. You cannot rely on a coma to tell you you're looking at an active body. You must check for subtle, dynamical signatures and weak gas lines, even when the images look stellar. Mission thinking also changed. Oumuamua sparked serious study of rapid response intercepts. Can we launch something fast enough to catch the next one? And creative proposals to use gravitational assists or solar sail-like maneuvers to chase down a target on a hyperbolic arc. Borisov helped refine the requirements for flyby instrumentation in a dusty, high-speed environment. Together, they shifted interstellar objects from curiosities to targets of opportunity in mission roadmaps. Keep designs modular, keep launch options flexible, and pre-bake trajectories that a future object could slot into with minimal redesign. If a third visitor arrives with enough warning, those studies could make the difference between watching from afar and sampling up close. Perhaps the deepest lesson is statistical humility. With only 2 well-observed examples, the space of possibilities is still enormous. Any single 3 I could look weird, not because most are weird, but because tales of distributions are fat when your sample size is 2. The right posture is to let each object shrink the uncertainty cloud. Catalogue what's similar, what's different, and which differences actually demand new physics versus new parameters. That mindset kept the discourse around Borisov sober and will keep the interpretation of any 3 I grounded, even if it presents a fresh puzzle. Tie all of this back to the planet-making theme and the path is clear. If a future visitor resembles Borisov, volatile rich, dust happy, it is an efficient spreader of sticky grains and exotic ices, exactly the kind of material that can tip marginal regions of a protoplanetary disk over the thresholds for concentration and collapse. If it behaves more like Oumuamua, compact coma or none, unusual dynamics, its gravitational and aerodynamic effects might be the bigger story. Wake-driven pressure bumps, gentle stirring that seeds instabilities, or delivery of rare minerals that alter sticking and cooling in subtle ways. Either way, the core operational guidance we earned from the first 2 stands. Find it early, characterize across wavelengths, chase the dynamics as hard as the chemistry, and keep multiple hypotheses alive until the data force a choice. In the end, Oumuamua taught us to be ready for the object that doesn't behave, and Borisov taught us to recognize the one that does. Between them lies the wide country where the next visitor will walk. If we meet it with the speed, breadth, and modesty those lessons demand, we won't just admire a passing light. We'll turn it into knowledge we can carry forward, knowledge that feeds our models of how dust becomes stone, stone becomes seeds, and seeds under the long patience of physics become worlds. Imagine a young star still wrapped in its soft hazy disk, a broad faint ring of gas and solids where day and night have not yet been invented, and weather is the slow migration of pebbles. Into this world, the interstellar traveller arrives. It does not need permission or a grand mass to matter. What it brings is timing, motion, and a cargo of dust and ice that did not grow up here. The passage is quick compared to the disk's life, but in physics, quick does not mean trivial. Like a ship cutting through a fog bank, it leaves a wake you can't see with the naked eye yet can trace by what happens afterward. First, delivery. Every vent of gas sprays grains. Every grain is a messenger. The object exhales water, carbon monoxide, carbon dioxide, and other volatiles that frost local dust and coat it with sticky mantles. It also sheds refractory specks, silicates, sulfides, flecks of metal, along with a varnish of reddish organics built in another sky. These particles are not evenly sprinkled. They fall into the disk along a corridor defined by the intruder's path, a ribbon of slightly enhanced solids meandering through gas that was previously uniform. Over time, orbital shear stretches that ribbon into an arc. Diffusion puffs it wider, but does not erase it. Months later, then years, that arc is still detectable as a place where pebbles are just a little richer in ice, a little darker with organics, a little better at sticking than their neighbours. Next comes structure, laid down by motion rather than chemistry. The traveller's gravity sculpts a pressure pattern in the gas, a mild high in front, a mild low behind. Dust and pebbles respond eagerly to such patterns, because pressure highs reduce the headwind that normally drives them inward. They slow, they gather. If the corridor of delivered dust overlaps a pressure shelf, the effect multiplies. The solids to gas ratio, call it Z, rises in patches. Crossing from Z approximately 0.02 to Z approximately 0.04 is not dramatic to the eye, but to the disk's physics it's a switch. The streaming instability becomes possible. Filaments of pebbles appear, then bead up, then collapse into planetesimals. 100,000 boulder-to-hill-sized bodies can be minted in the time it takes the visitor to vanish beyond the star's glare. Seeding is not only about creating brand new seeds, it also means feeding the ones already there. Imagine a handful of juvenile worlds, 100-kilometre chunks and moonlets, already prowling quiet orbits. The intruder's passage pre-sorts the pebble population into the aerodynamic sweet spot, where gas drag is strong. When those pebbles sweep past a juvenile, gravity and drag cooperate. The pebble's path bends, energy bleeds away into the gas, and the pebble spirals down to join the body. For a while after the encounter, accretion rates jump. A seed that would have starved grows chubby. A chubby seed crosses the line where pebble accretion becomes runaway. A runaway seed graduates to an embryo with the authority to reshape its lane. There is also the alchemy of snowlines. Disks contain invisible weather fronts, radial bands where water, CO2, CO, NH3, and other species flip between vapour and ice. Crossing a snowline changes how grains collide, how sticky they are, what sizes dominate. The intruder's outgassing nudges those fronts locally. A faint enrichment of CO or H2O shifts the temperature at which frost forms by a small but consequential amount. If the passage tracks near a snowline, delivered volatiles boost the number of ice-coated pebbles, exactly where pressure gradients already tend to form bumps. The result is a trap that's a little deeper, a little wider, and a lot more effective at stopping inward drifting pebbles. Where traffic jams, growth accelerates. Seeding can be subtle remodelling too. Consider the outer regions where turbulence is low and the midplane is a thin, dense sheet of sedimented pebbles. The traveller's wake compresses that sheet where it passes directly overhead, briefly raising midplane density and lowering relative speeds. In the same breath, it lofts wisps of dust at the flanks that cool, frost over, and rain back down as stickier snow. That 1-2, compress, then re-wet, leaves behind a midplane more hospitable to coagulation. No fireworks, no immediate planets. Just a rebalanced microphysics that puts the system a half step closer to a threshold it was already approaching. Not every effect points the same way. Stochastic stirring can raise collision speeds in some pockets enough to fragment fragile aggregates. But breakage is not failure in this environment, it is recycling. Fragments have more surface area per mass, radiate heat efficiently, and tend to refreeze thicker ice mantles. Feed them into a pressure bump and they become ideal pebbles again, small enough to couple to gas, large enough to drift into the trap, perfectly primed for the streaming instability to organise. In the best aligned cases, the golden passes, the chain is almost cinematic. A volatile-rich traveller crosses the outer disk when gas is still abundant. It outgasses strongly enough to dust a long corridor. Its gravity carves a lingering pressure bump. The corridor intersects a snow line. Pebble traffic jams. Z passes the threshold. Filaments form. A family of planetesimals is born. Some of those newborns fall into resonances with an existing embryo, pumping eccentricities that spark gentle mergers. Others remain as a belt, a reservoir of comets for future climates and oceans. The visitor continues on, but a signature remains. A new ring in millimeter continuum maps, a slight excess of carbon-bearing gas, a demographic shift in planetesimal sizes. A million years later, the system will not remember the traveller, but its architecture will. Even without new births, the intruder can deliver personality. Worlds inherit the flavours of the pebbles that built them. A corridor enriched in organics biases surface albedos and atmospheric chemistry. A dusting of sodium or potassium changes melting points and volcanism. An infusion of sulfur compounds sculpts future hazes and cloud decks. A planet built mostly from local, water-poor pebbles, but seasoned by an interstellar sprinkle can end up with enough volatiles for shallow seas where none were expected. Seeding, in this sense, is culinary. The base ingredients are local, the spice rack is visiting. Seeding also operates through time. The corridor of delivered grains does not stay put, it shears into a spiral and slowly diffuses. That spiral intersects different neighbourhoods on successive orbits, igniting short-lived episodes of enhanced accretion as it sweeps by. A juvenile that was unlucky last time gets a feast this time. Over tens of thousands of years, the spiral fades, but its work is cumulative. A little ring more sculpted here, a few more planetesimals there, a small trend toward larger embryos in one quadrant of the disk. Architecture accretes from nudges. Very rarely, the interloper is slowed enough by gas drag and dynamical friction to become loosely bound for a season, looping the star on a wide, decaying arc. That temporary capture is a festival. Each preapsis, the body revisits the same annulus of the disk, reseeding it, recarving the pressure pattern, refeeding any embryos lurking there. A handful of such passages can transform a quiet lane into a construction site. When the visitor finally escapes, the ring remembers. What about the statistics? An individual system may never experience such a pass at just the right time, but the galaxy is vast and noisy. Star-forming regions are crowded. Young systems toss debris by the billion. Passing stars and clusters stir orbits. Over millions of years, the probability that at least a few interstellar objects thread a given disk while it's young and gas-rich is not negligible. Multiply by the number of disks and seeding shifts from curiosity to background process, small individually, decisive in aggregate. The universe is built on many small causes. From the point of view of observers, seeding leaves clues. A young disk might show asymmetric rings, kinks in spiral arms, or transient arcs of increased millimeter brightness, all signs of a localized solid's excess. Chemistry maps could reveal a streak of elevated CO or HCN, not aligned with any obvious planetary wake. Polarimetric images might show a change in dust grain sizes along a path, consistent with fresh, fluffy aggregates. None of these alone proves a visitor past, but together, and in the absence of a bound perturber, they whisper of a brief guest. There are failure modes worth noting. A visitor that is too large and too fast could overstir a fragile disk, heaten it and boost in fragmentation beyond what pressure bumps can heal. One that arrives too late after the gas has mostly cleared will deliver dust that won't be trapped efficiently, smearing out into a low-contrast veil. One that carries little volatile inventory will carve a gravitational wake but supply no sticky mantles to exploit it. Seeding, like gardening, is seasonal. Yet when the season is right, the metaphor is hard to resist. A passing hand crumbles a pinch of soil into a furrow, drops in a few foreign seeds, and moves on. The rain and sun, drag and pressure, turbulence and gravity do the rest. Years later, there's a line of trees where there would have been scrub. In a planetary nursery, the trees are planetesimals and embryos. The line is a ring bright in pebbles. The years are a few thousand orbits, and all because something from another sky left a trail of difference behind. In that sense, 3i Atlas, or anything like it, does not need to be a planet maker in the heroic singular way. It is enough to be a planet enabler. The disk is already a machine for turning dust into worlds. Thresholds and traffic govern its pace. A visitor shifts the traffic, deepens a trap, sweetens the collisions, and lets the machine run more efficiently along a track it was already poised to take. The traveller keeps going. The system stays changed. Somewhere down the line, a young world counts that nudge among the 1,000 quiet favours that let it exist at all. Begin with the simplest instrument of all, brightness over time. Take repeated images and build a light curve, the object's flux measured night after night, hour after hour as geometry and activity change. If the nucleus is bare or the coma faint, the light curve carries the spin. A periodic rise and fall as elongated facets rotate sunlight toward and away from us. If the coma is strong, the curve tells a different story. Outbursts, jet cycles, sublimation that waxes and wanes with solar heating. The trick is to separate the point-like nucleus from the fuzzy glow enveloping it. Astronomers pick small circular apertures for the nucleus and a newly for the background. Apply aperture corrections to capture the same fraction of the point spread function each time and stack short exposures to beat trailing. Done carefully, the light curve yields a rotation period, a lower limit on the shape's elongation from the amplitude, and any non-repeating weather on the surface, fractures that open, jets that flick on, vents that fade. Astrometry, the precise position on the sky, looks mundane, yet it is a goldmine. Fit those positions with a purely gravitational orbit, and then ask what's left in the residuals. If the object is outgassing asymmetrically, sunlight heats one side more than the other, jets push gently, and the path deviates by milliarc seconds that add up to a measurable, non-gravitational acceleration. Modelling that residual with standard sublimation laws, water driving near the sun, CO/CO2 farther out, constrains which volatiles dominate and where the active areas sit on the surface. Even without seeing a single molecule, the dance of the trajectory tells you that gas is there, and hints at how much. Colour is a quick probe into composition and grain size. Through broadband filters, G', I''Z', or BVR, the object's spectrum becomes a handful of points. Is it red like many organics-rich comets, neutral like silicates, or curiously blue from an abundance of fine, forward-scattering dust? Colour slopes shift as the coma evolves. Fresh fluffy grains can redden the light. Radiation and solar heating can darken and neutralize over days. Map colour as a function of distance from the nucleus, and you see grain evolution in flight. Large, compact particles clinging close in. Smaller, more porous ones carried far by gas and solar radiation pressure. Spectroscopy takes the next step and splits the light into thousands of narrow channels. In the optical, classic comet bands appear if the object is active. CN near 300 at 88 nanometers, C2 around 516 nanometers, C3 around 405 nanometers, a forest of NH2 features, and the broad, sunlit continuum of dust. In the near-infrared, overtone and fundamental bands of H2O, CO2, difficult from the ground but tractable from space. CO, CH4, and organics reveal themselves. At thermal infrared wavelengths, emission from warm dust peaks, giving grain temperatures and size distributions. Each line's strength, width, and Doppler shift carry information. Strength gives production rate. Width and line shape give expansion speeds and possible jets. Shifts map bulk flow relative to the nucleus. Combine line fluxes with a Hazer or vectorial model for photochemistry, and you can infer parent molecules upstream of the radicals you observe: OH whispering of water, CN of HCN or other nitriles, C2 of more complex organics. Polarimetry turns scattered sunlight into geometry and texture. Dust grains polarize light as they scatter it. The degree and angle of polarization versus phase angle, Sun-Comet Observer, encode the typical size, porosity, and composition of the particles. Interstellar visitors with unusually porous or fresh grains can show polarization curves offset from our local family comets. Map polarization across the coma and jets pop out as strands with distinct grain properties, fresh particles, less processed, carrying the accent of the vent that launched them. High spatial resolution, adaptive optics on large ground-based telescopes or space telescopes doesn't always resolve the nucleus, but it sharpens the inner coma. With that clarity, you can see sunward fans, corkscrew jets from processing active regions, and sharp brightness gradients that betray collimated outflow. Fit those structures with Monte Carlo dust dynamics. Assume a set of vents, launch speeds dependent on grain size, include solar gravity and radiation pressure, and tune the model until synthetic jets match the observed ones. The fitted vents become longitudes and latitudes on the nucleus. The launch speeds set the gas flux. The grain size slope, often a power law, falls out naturally. Thermal infrared is the realm of temperature and true size. If the coma is weak or can be modelled, mid-infrared flux combined with a thermal model, NEATM, or more advanced beaming, thermal inertia treatments, yields the effective diameter and albedo of the nucleus. A high beaming parameter hints at rough, blocky terrain. Low thermal inertia suggests a fluffy, insulating regolith, both consistent with cometary nature. If the coma dominates, its thermal spectrum still tells you average dust temperature, which, when compared to blackbody expectations, encodes grain size and composition. Small grains run hotter, silicates and carbon radiate differently. Spectral features, the 10 micrometer silicate band, reveal crystalline versus amorphous content and the presence of olivines or pyroxenes, fingerprints of thermal history in another star's nursery. Millimeter and submillimeter arrays, like ALMA, turn the coma into a map of molecules. Rotational transitions of CO, HCN, H2CO, CS and others trace density and velocity fields. Velocity-resolved channel maps show outflow cones and day-night asymmetries. Excitation analysis gives realistic gas temperatures and collisional regimes. Isotopolog lines, 13CO, HC15N, pin down isotopic ratios, D over H in water, 12C over 13C in carbon species, 14N over 15N in nitriles, which are the closest thing to a return address you can hope for without a sample. A D/H ratio matching or diverging from typical solar system comets says whether water chemistry in the source system followed familiar paths or not. Occultations, when the object passes in front of a background star, are the stealthiest of all. Organise a network along the predicted shadow path, record the star's light at high cadence, and watch for the brief dip as the nucleus, or dents in a coma, clips the starlight. Multiple chords from different observers reconstruct the silhouette, a direct constraint on size and, if lucky, shape. A thin, extended coma can also leave a telltale softening of the star's light curve, constraining dust density profiles at scales too fine for direct imaging. Occultations are unforgiving in timing, but pay off with kilometre precision sizes that anchor thermal models and mass estimates. The humble quantity AFR condenses a lot of dust information into one number, Measured from the surface brightness of the coma at a given aperture radius RHO, it scales with dust production independent to first order of aperture size and geocentric distance. Track AFA as a function of heliocentric distance and phase angle, and you get the dust activity law, how the coma breathes as sunlight rises and falls. Deviations from smooth power laws signal outbursts, seasonal effects on a spinning tilted nucleus, or compositional transitions as different ices take turns driving. Time is the quiet axis that makes everything legible. A single spectrum is a snapshot, a cadence is a story. Watch gas lines strengthen before the dust continuum, and you catch the lag between sublimation and dust lifting. See dust colours redden after an outburst, and you witness large grains falling back while fine grains escape. Sample a wide range of phase angles and you build the phase function, how bright the object looks at different sun observer geometries, which carries information about surface roughness, if the nucleus is seen, and dust scattering physics, if the coma dominates. Sample inbound and outbound legs, and you expose hysteresis, surfaces that remember heating, or subsurface layers that must thaw before they flow. All of this rests on careful craft, non-sidereal tracking to keep a fast mover centred, short exposures stacked with shift and add to prevent trailing loss, sky frames and coma models to remove faint diffuse backgrounds, absolute calibration with standard stars, and robust uncertainties so models don't fool themselves. For faint interstellar visitors, observers lean on global coordination, small telescopes for nightly light curves, big glass for deep spectra and high resolution, radio arrays for gas, space assets for mid-IR and CO2, citizen scientists for last-minute occultation cords when a path crosses roads and rooftops rather than mountaintops. When the data streams meet, they cross-check. The non-gravitational acceleration inferred from astrometry should match the gas production implied by spectra, given a plausible active area and recoil efficiency. Jet geometries from high-res images should be consistent with light curve periods and pole solutions from inversion. Thermal sizes should agree with occultation silhouettes. F-row trends should echo dust mass loss rates derived from thermal continuum. Where they don't, the mismatch is the clue. Perhaps grains are fluffier than assumed. Perhaps activity is confined to a few vents. Perhaps an insulating crust throttles heat. Sometimes the best clue is the absence of a signal. A flat optical spectrum with no gas bands limits volatile output. A thermal flux that's too low for any reasonable nucleus size demands high albedo or a coma-dominated scene. A light curve that won't repeat implies tumbling, non-principal axis rotation, which in turn hints at a recent torque, outgassing, or a fragmenting event. Even radar, usually hopeless for such distant and small targets, can play a role if a visitor wanders close enough. Echoes constrain bulk reflectivity and surface roughness, discriminating icy rubble from metallic rock, unlikely for an active interstellar body, but worth listening for. In the end, clues in the light is not a metaphor but a workflow. Photons carry momentum, spectra, polarization, timing, geometry. We turn those into rotation, size, composition, grain physics, event maps, outgassing laws, and, most delicately, origin stories encoded in isotopes. For a fleeting traveller like 3i Atlas, the window is narrow, so the choreography matters. We watch the brightness beat to infer a spin. We split the light to let molecules speak. We weigh the push on its path to hear unseen jets. We sharpen the glare until fans appear. We catch a star winking out to draw a silhouette. We stitch inbound to outbound to see memory in ice. Each method alone is a hint. Together they become a biography. What the object is, how it behaves under a new sun, and which parts of a distant unseen planetary nursery it remembers in the light it throws our way. Close your eyes and imagine the galaxy not as a silent expanse but as a slow conversation carried by dust and ice. Stars form, live and die. Disks blossom and thin, worlds congeal and cool, and throughout it all small bodies wander. They are the couriers of that conversation. Each carries a packet of chemistry written by a particular star's light, a particular disk's temperature ladder, a particular history of shocks and stillness. When one of those couriers brushes another system, it delivers not doctrine but dialect, a handful of different grains, a shift in isotopes, a flavour of organics that did not grow up here. The question is simple and enormous. Are we in any degree children of those wanderers? Begin with the unromantic answer. Planets can form perfectly well from the stock their own disks provide. The physics of sticking, trapping, concentrating and collapsing pebbles does not require foreign seeds. Gas and dust know how to become worlds with no help. But independence is not the same as isolation. A disk poised near thresholds is exquisitely sensitive to small nudges. A young world's chemistry can be biased by just a few % change in what falls upon it. In that sensitivity lies the opening for interstellar exchange to matter, not as an all-or-nothing cause, but as a shaper of probabilities, a quiet hand on the scales. Consider the raw ingredients of life as we know it. Water, carbon-rich organics, nitrogen, sulfur, phosphorus, a suite of metals and energy gradients to push reactions uphill. None of these are rare in the galaxy. All of them occur in comets and soot-like dust. Wanderers are natural thermoses for such compounds. Deep inside, porous ices shield fragile molecules from radiation. Surface crust can grow tough and carbonized, turning into a heat shield during brief sunward jaunts. When a traveller exhales into a young disk, it doesn't deliver blueprints for cells. It delivers monomers, catalysts and glue, alcohols and nitriles, amines and carboxylic acids, ring structures that can stack and absorb light, metal grains that catalyze hydrogenation and dehydrogenation. Those are not life, but they are the kind of parts that make prebiotic chemistry more likely to get traction when they settle into warm ponds of rock and ice. Now think less about chemistry and more about architecture. Worlds are not made once, they're remade repeatedly by late delivery. Comets and asteroids that cross the lanes of growing embryos and young planets. If, in the churn of early orbits, interstellar wanderers occasionally join the traffic, they become part of that late veneer. A planet's first ocean might be a local accomplishment, but its trace salts and volatile balance could bear the fingerprints of foreign dust. A moon's haze could owe its unusual colour to a surplus of carbon-rich grains delivered by a passerby millennia earlier. Even tiny differences matter. An extra % of water in one planetesimal family means a more persistent hydrosphere after volcanic degassing. A slightly sulfur-richer feedstock makes for different climate feedbacks once sunlight begins to interact with outgassed skies. There is also the possibility, whispered about since the 19th century and reformulated with modern restraint, panspermia. The cautious version doesn't imagine fully formed organisms cruising the void on open decks. It asks rather whether robust spores or encapsulated microbes, if they exist elsewhere, could survive interplanetary or even interstellar transfer embedded deep in rock or ice. Shock, cold, vacuum and radiation are formidable, but not uniformly lethal. Labs on Earth have taught us that some spores and microbes endure insults that would flatten complex life. The transfer times between nearby stars are long, yet not impossibly so for dormant biology under meters of shielding. No one can claim on present evidence that life has crossed stars, neither can anyone close the door on the physics outright. If the probability per object is tiny but the number of objects is immense over billions of years, the prior is not zero. Sensible minds keep that window cracked, not for romance but for completeness. Even without smuggling anything living, wanderers could carry informational biases, recipes rather than organisms. Imagine a body whose interior chemistry, over eons of gentle heating and cooling, has stumbled onto efficient pathways for building certain polymer precursors. It arrives, vents, and sprinkles the disk with a distribution of molecules skewed toward those pathways. On a young world where wet-dry cycles, mineral surfaces, and UV light are doing the slow work of selection, that skew could hasten the climb out of the chemical flatlands. In that modest sense, we would indeed be children of wanderers. Our origin chemistry was tilted towards success by imported kits. Zoom out to galactic scales and an emergent picture forms. Star-forming regions are crowded. Close passes between stars are common early in their lives. Planetesimals are ejected by the trillions as giant planets grow and rearrange orbits. The Milky Way is, in effect, a mixing bowl. Material doesn't just move once in a while, it circulates. And circulation creates a kind of chemical averaging. Disks borrow from one another, and over long times the range of possible starting soups for planets narrows. That doesn't erase local personality. No two kitchens use spices in the same way, but it reduces the odds of truly exotic outliers. If that averaging is real, it could explain why some exoplanet atmospheres we've measured look familiarly carbon and oxygen heavy. Why comets in different systems might share broad traits. We are not just our parents' children. We are also the nieces and nephews of the neighbourhood. There is a counter-story worth holding alongside this one. Selection can harden differences just as mixing can blur them. Suppose two nearby birth clusters have slightly different metallicities or radiation environments. The small bodies they export will carry those signatures, and their recipients will inherit small biases in, say, the ratio of carbon to oxygen or the availability of nitrogen. Those biases can drive worlds down different climatic basins of attraction. Carbon-poor disks favour rocky, thin-atmosphere planets. Carbon-rich disks tilt toward hazes and hydrocarbon seas. Nitrogen-rich conditions make certain prebiotic networks more tractable. If you map the galaxy not by stars alone but by the slow eddies of small body exchange, you might find neighbourhoods where particular kinds of worlds are more probable. In that sense, whether we are children of wanderers depends on which eddy we grew up in. Bring the question home. Earth's early history is a tapestry of bombardments and calm, oceans and magma, lightning and quiet rain. In that story, comets and asteroids delivered water, organics, and metals after the planet's initial differentiation, enough perhaps to tip the balance toward persistent liquid water and a thick, reactive atmosphere. Were any of those messengers interstellar, we don't have a smoking gun, but we do have a principle. If even a tiny fraction of late delivery mass came from outside the solar family, it could have nudged the concentrations of key volatiles or trace metals by amounts that matter to climate, crust chemistry, and ocean salinity. When life finally learned to write itself into polymers, to copy and air and remember, it did so in an environment pre-shaped by countless small accidents. A few of those accidents may have begun under another sun. There is also humility in the arithmetic of time. Our species is young, our instruments are younger. We have recognised precisely 2 interstellar interlopers with confidence, and already they have stretched our imagination of what the small body zoo contains. It would be hubris to declare that such visitors could not have influenced the deep past, because we have not yet caught one in the act of seeding a disk. We observe for decades. Disks live for millions of years. Planetary systems traverse the galaxy for billions. A process can be rare on human timescales, and yet common in the ledger of worlds. If the galaxy does exchange materials efficiently, there's an odd corollary. The search for life's signatures elsewhere becomes, at the margins, the search for our own extended family. Not because someone seeded us with intent, but because the same dust that once floated through our nursery may have drifted through another, and the same biases that tilted our chemistry may tilt theirs. When a telescope someday catches the spectral breath of a distant ocean world, blue-green light filtered through oxygen and methane in tension, we might be seeing a cousin, not by blood, but by dust. And what of the philosophy in the background, the question of belonging? To think of ourselves as children of wanderers is to adopt a middle path between isolation and destiny. We are neither insulated accidents nor the inevitable flowering of a single garden. We are the outcome of a system that listens to small visitors and remembers them in stone and water. That view is both sobering and liberating. Sobering, because it insists that our origins include contingency upon contingency. If one disk eddy had been weaker, if one corridor of dust had been poorer in organics, if one late delivery had missed, liberty, because it broadens our kinship. We are related to more than one star. Finally, imagine a future where we sample one of these travellers, scoop grains, measure isotopes, sequence the long molecular rubble inside, and compare the record to our oldest rocks. If we find molecules that rhyme with the earliest organics on Earth, if their isotopic quirks are echoed in ancient zircons or cometary inclusions, we will have proof not of a single origin story but of a shared pantry. If we find utterly alien chemistries, silicon-heavy organics, nitrogen frameworks unknown to our biochemistry, we will have learned that the conversation is wider than our dialect. In either outcome, the answer to the question softens from a yes-no to a spectrum. We are in some measure local children, in some measure children of wanderers, and in all measures children of a galaxy that never stops trading small gifts with itself. On the outbound leg, everything feels like a mirror turned gently backward. The heating that once woke vents now slips behind the horizon of possibility. Sublimation slackens, jets sputter. The coma thins into diaphanous breath and then to almost nothing. Dust that was launched at different speeds sorts itself under two quiet forces, solar gravity and radiation pressure, stretching into a fading Sindine synchrone tapestry that only careful imaging can still pick apart. The tail, once a living weather report, becomes an archive of past days, coarse grains lingering near the path, fine ones swept far and slightly sunward, each parcel of powder a timestamp of when and how fiercely the nucleus last exhaled. Astrometry grows calmer as the recoil from outgassing dies. The tiny non-gravitational acceleration that once nudged the trajectory now dwindles towards zero, leaving a pure hyperbola to integrate into far future ephemerides. If the body had been tumbling, the thermal torques that can sometimes damp or pump a spin state lessen. The rotational light curve, which may have stuttered through outbursts, returns to the metronome of shape alone. In that steadiness there's a kind of farewell handshake, a last clean measure of the object's bulk properties before it slips under the limits of our instruments. The science doesn't end when the signal does. Photometry stacks into rotation solutions, spectra knit into production rate laws, polarimetry curves feed grain porosity models, millimeter maps invert into outflow geometries and isotopic ratios. Teams cross-compare. Is the gas we inferred from trajectory residuals consistent with line strengths? Do thermal diameters agree with silhouette chords from chance occultations? Do jet models respect the pole orientation implied by the light curve? Where they don't, the mismatches are precious, forcing refinements to assumptions about beaming parameters, vent latitudes, or grain size slopes. A traveller's last gift is often a set of stubborn residuals that improve our tools for the next encounter. Some of the dust will keep telling the story without the nucleus. Large grains, launched gently, slide into the interplanetary background as a diffuse trail that machines like wide-field surveyors can still find for a while as a pencil-thin enhancement along the outbound arc. Very rarely, geometry may scatter fragments toward a planet's hill sphere. Most will miss, but a non-zero handful might touch an atmosphere years hence, as meteors so rare they will never be recognised as interstellar in origin. More plausibly, a fraction of the slowest grains will be perturbed by the giant planets, diluted into the zodiacal complex, their provenance scrambled. Even in disappearance there is remixing. As the object dims past the reach of modest glass, the baton passes to the keepers of long memories. Survey pipelines freeze the last detected positions. observers upload reduced frames and raw stacks. Spectral calibrations and flat fields join public archives. Reduction scripts and notebooks, messy but invaluable, are pushed to open repositories. Students who began the campaign as novices now know the smell of saturated pixels, the patience required to chase a baseline through thin cirrus, the care it takes to propagate a 1 sigma uncertainty without optimism. A faint intruder leaves behind apprentices who have become practitioners. There is a different kind of legacy too, the rehearsal. Each object compels a test of the network, discovery, vetting, target of opportunity requests, coordination across longitudes, switching filters midnight because a gas band flared, phoning amateur observers along an occultation path with minutes to spare. Weak spots always reveal themselves. A cue that couldn't flex, a weather loss that no backup covered, a gap in wavelength where the story would have been clearest. The outbound fade is when those are written down and fixed. The next time the sky sends something hyperbolic, the machine will run smoother, faster, kinder to the truth. Engineers take their own notes. If the trajectory popped into view with enough warning, mission planners will have run playbooks for rapid intercepts. Solar Obeth arcs that dive close to the sun for a speed boost, gravity assists chained like pearls, solar sails that trade time for delta V, even the speculative shove of beamed light on wafercraft. Those designs aren't wasted if they weren't flown, they become templates with margins already carved. The long goodbye is also a long hello, to architectures that can be launched on short notice, to instrument suites tuned for dusty, fast flybys, to guidelines that keep safe standoff distances when a coma turns out richer than predicted. Culturally, an interstellar passerby changes how a sky looks even to people who never see it. A headline, visitor from another star, lodges in imaginations. Planetariums add a new dome show. A classroom project watches the brightness taper night after night. There is humility in that taper. Not everything we want to know can be known on our schedule. The universe offers windows, not guarantees. Accepting that truth without resignation is part of the craft. We learn to squeeze signal from the dim, to say insufficient when it is, and to resist glossing absence with certainty. Modelers get busy when the photons stop. The entire encounter becomes initial conditions. A shape and spin solution here, a production law there, a handful of isotopic constraints on top. Into the code it goes, gas-dust hydrodynamics for jet morphology, thermophysical models for skin depth lags, Monte Carlo suites for dust trails under radiation pressure and planetary perturbations. Sensitivity analyses explore the nearby parameter space. What if grains were fluffier? What if vent latitudes were swapped? Which assumptions create observables that would have looked different enough for us to notice? Those answers flow backward to observers as recommendations for the next time. Prioritize this band, this cadence, this phase angle coverage. Against the quiet exit runs a speculation as old as curiosity. Where was it born, and where now? Backtracking the hyperbola through the sun's motion, and the local standard of rest yields a cloud of possible pasts, broadened by the tiniest measurement errors and any unmodelled thrusts. Forward integration yields a future measured in parsecs and centuries, a pass through the outskirts of a moving group, an approach not especially close to any catalogued star, a return to anonymity in the thick disk. There's a strange comfort in that ordinariness. The galaxy is not short of places to be from or places to go. A traveller's dignity is not in a named destination, but in the fact of motion itself. If the object left behind an unsolved puzzle, a non-gravitational acceleration just a shade too large for the measured gas, a colour slope that refused to match known dust analogues, of D/H ratio that sat impishly between families, that riddle becomes a standing invitation. Laboratory groups will bake and irradiate ices with exotic mixtures, flexing porous samples to see how crack networks drive jets. Spectroscopists will hunt faint bands that might have been missed. Instrument builders will argue for detectors whose noise floors can finally hear what the last campaign could only suspect. The long goodbye of a specific body stretches into a long apprenticeship to a question. There is, of course, a more personal ending built into all of this. People lost sleep to chase a faint smear of photons, called in favours for telescope time, stayed up to shepherd raw bits into clean spectra. They argued over baselines and background subtraction, over whether that bump was an outburst or a cloud passing through the edge of the field. When the plots flatten and the knights move on to other targets, what remains, besides the papers and data sets, is a shared memory of a thing briefly real in their lives. The sky is not a stranger to those who have tried to hold something ephemeral steady in a guiding box. Pull all of it together, and the goodbye becomes less an ending than a handoff. From object to archive, from measurements to models, from this visit to the readiness for a next. We know a little more now about how faint activity masquerades as stillness, about how dust talks in polarization, about what we need to measure first when time is short. We have a better feel for thresholds in disks, for the little physics that can make big differences when a wanderer crosses a nursery. We possess, too, a renewed appetite, not just to wait for the sky to bring us something, but to meet it halfway with instruments tuned, teams primed, and humility intact. And then there is the simplest truth. It keeps going. The nucleus slips past our last magnitude limit and continues into a darkness that is not empty to it, only quiet. The sun becomes a star among stars behind it. Our whole planetary family with all its stories collapses into a single point of light. If you track it in your mind's eye, the object is still the same. Rock and ice, voids and veins, the memory of other warmths, turning slowly, cooling, carrying its private library through a galaxy that is forever swapping footnotes with itself. We let it go because there is nothing else to do. We let it go knowing that what mattered most stayed, the changes in us. We will look up again with steadier hands. We will be kinder to our uncertainties. And when the next interstellar intruder writes its first faint line on our detectors, we will already have begun to read. If you're still awake with me here at the edge of the dark, breathe once more and let the sky settle. We began with a rumour, an interstellar whisper named Three-Eye Atlas, then followed that whisper as it crossed the quiet lanes of our sun. We watched dust learn to stick. We listened as gravity's soft hand gathered pebbles into threads, and threads into seeds, and seeds into the first sturdy shapes of worlds. We traced faint bands of light to their source, read the small clues they carried, rotation and colour, gas and grain, warmth and silence. And we asked the oldest question of all, how do new things begin? Maybe the answer is simpler than it looks. Maybe new things begin the way dawn begins, not with a single bright event, but with a series of gentle thresholds. The dim that becomes grey, the grey that becomes blue, the blue that, almost shyly, admits gold. An interstellar traveller does not arrive to sculpt a planet by itself. It arrives to tip the balances already poised inside a disk. A soft wake where dust lingers a heartbeat longer. A pressure shelf where the headwind pauses. A ribbon of exotic grains that make collisions kinder. A small correction in a long arithmetic. And then the disk, which has been practicing patience for 1,000,000 years, says, "Thank you, I can do the rest." If you press your ear to that patience, you'll hear other, quieter truths. That the galaxy is not a museum of sealed rooms, but a commons with footpaths and breeze. That stars do not hoard their materials, they shed and share them. That the chemistry of one nursery can walk across space, and, on some lucky evening, meet another nursery halfway. That there is kinship hiding in the dust. We are local, yes, children of this sun, of these rings and shelves and snow lines, but we may also be the inheritors of a few borrowed spices stirred in so long ago the spoon has been forgotten. To me, that does not make us less, it makes us more. It also makes the faintest observations feel tender and urgent. Every pixel we stacked, every spectrum we coaxed out of the dark, Every bet we made that a smudge was not a cloud or a cosmic ray. Those not just measurements, they're acts of welcome. You are far from home, they say to the traveller. Come in, warm yourself a moment on our star. Tell us what you remember of your sky. Sometimes the answer is loud, jets, bands, tails, motion that won't quite obey Newton unless you let a little gas push the path. Sometimes it's quiet, no tail, no lines, just a light curve that lopes like an animal with secrets. Either way we listen, and listening changes us. There's something else the visitor leaves that we don't often name, better questions. We ask them in different rooms, in laboratories where ices are baked and cracked, and made to sing under lamps that mimic distant suns, in code where equations are taught to whirl and cool and collide until filaments bloom on a virtual midplane, at telescopes where we try to point a little faster, calibrate a little truer, coordinate a little kinder. The sky is an excellent teacher because it never instructs directly. It sets a problem and then steps out of the way. We do not solve the problem, we grow into it. And as we grow, we get gentler with our certainties. The more we learn, the more we admit the shape of what we don't. We stop demanding that every comet wear a textbook tail to be considered real. We give space to the possibility that some ices hide cleanly, that some grains are so porous they feel sunlight as a shove, that some spins are so complicated they refuse to repeat on cue. We plan for both the loud and the quiet. We prepare to be wrong usefully, and we practice changing our minds with grace. That too is part of a good night sky, its insistence on humility. And so we come to the soft parting. 3i Atlas dwindles, the numbers settle into the archive, the notebooks close, the plots cool on our screens. But if you step outside, right now or later, or in a season when the air has the taste of first snow, you'll find that parting is the wrong word. The traveller is still out there, smaller to us, not smaller to itself, carrying its private library into the larger dark. Our sun is behind it, a single pin among many. Ahead of it, no destination we can point to, only more night threaded with future chances. That is not loneliness. That is belonging scaled to a galaxy. Keep what you like from tonight. Keep the idea that worlds start as a rumour shared among dust. Keep the picture of a pressure bump catching pebbles like a gentle hand. Keep the thought that a corridor of foreign grains can sweeten a disk's collisions just enough for sticking to win. Keep, too, the human pieces, the first detection ping that quickened a heartbeat, the scramble to schedule an instrument, the quiet delight when a faint line rose where you hoped it would, the laugh when a wind gust tried to erase an entire night, and you outstubborned it. These are as much a part of the story as any formula. If you make things, videos, songs, poems, circuits, bread, maybe this is the part where the cosmos hands you a small mirror. Planet making is craft. So is what you do. It happens in thresholds. Not much, and then suddenly a form that holds. It happens with help you did not expect. A book you found at the right hour, a friend's sentence you can't stop turning over, a stranger's work that made a corridor of possibility through your week. It happens in the patient company of small errors that teach you what the final thing needs. Dust to pebble, pebble to seed, draft to take to something that knows how to glow. Before we fold the night, let's name the simple comforts. The universe is allowed to be generous. It is allowed to be noisy with small bodies that cross the gaps between stars. It is allowed to seed, to stir, to remix, to make futures more likely without anyone noticing the moment when not yet became now. And you are allowed to stand beneath all of that and simply feel a quiet pride that the species you belong to learned to hear a whisper from another sun and answer with curiosity instead of fear. If your eyes are heavy, let them be. The sky will continue without your supervision. Somewhere a telescope is still tracking, a script is still writing dates into a file name, a comet's faint fan is still teaching photons how to travel for us. The rest can wait until morning. When you wake, the story will be where you left it, just a little longer, just a little deeper, just a little kinder. Because that is what these visitors do. They pass through and leave small differences behind, in discs, in data, in us. Thank you for drifting here with me tonight. If you want to wander again, you know where to find me. Somewhere between the hush of the dust and the first step of a new world, watching for the next faint line that says softly, "I came from far away. May I tell you what I saw? Sleep well, traveller. The stars will keep."